You can share your slides right now.
Well, good morning, good afternoon, or good evening, depending on your time zone and latitude. And congratulations for 46 years of service to the community and interesting talks. I hope this adds to your portfolio. So I'm going to share the uh, the desktop here, and I'm going to go into full screen mode. Hopefully you can see that.
Yeah.
So, the talk, my talk is on the Grand Coding Challenge, finding a new largest known prime. This is part of a great indoor sport of hunting, as alluded to Dennis, and hunting for world record size prime numbers. This is going to be a highlight of a tutorial I give, and the URL is below. I believe also it'll be in the meeting notes for the full details. So if there's things you want to look at in more detail, and of course you're free to contact me as well. So the so first I say, what is a prime number? It's a natural number like 1, 2, 3, 4, 5 that is prime if and only if it has two distinct natural number divisors, one in itself. So I list here the first 32, there are 25 primes less than 100. 6 is not prime because you can also get it by multiplying by 2 times 3. So the largest known prime is pretty big. It's 2 to the 136,279,841 minus 1. It tops in over 41 million decimal digits. That would be about 8,205 pages. And then the English name is the first time that we've had a known prime whose English name weighs in over 1 gigabyte, using the method that mathematician Conway and I developed for naming English numbers of any size. It would require you about 136 reams of paper, double-sided, to print. And we figure normal speech patterns, it would probably take you about 7 years of continuous speaking just to say it. So they have the largest known prime is pretty big. Now, in this item here, um, whoops, let's go back to this spot and go back to here again. So in here, I should mention there is no largest prime. There's only a largest known. There you can always break the record, and you can see the proof in the tutorial. Now, I mentioned to say that it's a natural number who has only two distinct natural number divisors. And you might think, well, okay, the way you find a prime is you try to factor it. And yes, you can do that. But the problem is that the technology of finding primes, this technology for factoring, are pretty disjoint and only overlap over the method of, look for a factor. If you don't find any and it's only one in itself, it's prime. That's the only way they interact. Otherwise, they're fairly distinct. And factoring is fairly difficult to do. The 2022, the world record was 320 digit number for generalized number for factoring, whereas probability tests are now pushing 41 million decimal digits. The last time that someone factored a number and found a record prime was in 1951. So we've had 7 years of these new probability tests. And again, the factoring is so slow, you're not going to get a record prime by merely factoring. Now, the first time a record prime was found without factoring, and it was done by hand, was by a very famous mathematician, Luca, who proved 2 to the 127th power minus 1 was prime. So that number you see there is prime. He did it not by factoring in 1876, but he established that it had a property that only primes of the form 2 to the power minus 1 had. So again, he didn't factor it. He said, this has a property that only primes have, therefore it's prime. Now, what he developed a lot of work in mathematics in Lucas sequences. So you might have heard of the famous Fibonacci sequence. And this is the thing where you start with 1, 1, and you add the two together to get 2, and then you take the last two, 1 plus 2 to get 3, 2 plus 3 is 5, 3 plus 5 is 8, and so forth, right? That's that's a very specific sequence, has some nice properties. But Luca expanded to say, starting with any two values, do the same kind of repetitive addition. And Luca numbers are particularly interesting because his this particular sequence starts with 2, 1, not 1, 1. So you do 2 plus 1 to get 3, 1 plus 3 to get 4, 3 plus 4 to get 7, and so forth. And it turns out these Lucas numbers are very useful for primality testing. Now, there is an interesting property. So in this thing here, I have I'm a spreadsheet. I start with 2, 1, and then basically each row I'm basically adding the previous two. And this is the sequence number starting with 0. And you notice that when I'm on a prime number row, if I take the Lucas number, divide by the row number, I get a 1. In fact, all primes are this property. If it's a prime, the prime divided, the Lucas number for that divided by it leaves you a remainder of 1. And you can think, okay, so I can find its prime by there, except that while all primes have this property, there are pseudoprimes, things that are not prime that also satisfy it, like 705 satisfies it. So you can't quite get a proof, but it's an interesting example of a property. Now, you could try to do this for using Lucas sequences to find stuff. The problem, of course, is that there are a bunch of fakers in there. Also, it takes a long time to just repeatedly add it. If you wanted to prove, if you were to try to test whether something on the order of a trillion was a Lucas prime, you'd have to do a trillion sequences. But fortunately, there's shortcuts, and one of the shortcuts is you can jump ahead. So if you know like term number 4, you can immediately do number 8 by squaring the 4 term, subtracting 2. So this table shows you powers of 2 where you jump by squaring in -2. Of course, the number gets big, but you can jump ahead quite fast. And there's other sequences like that you can do to sort of jump around. You don't have to do it repetitively. And in 1930, a very prominent mathematician, D.H. Lamer, had his thesis work where he extended Lucas' work, and he had what's now known as the most efficient proof of primality known, that there's a work relative to the proof is prime versus the size. And it was my great honor to actually to study under him. But he created what's called the Lucas-Lamer test. Remember, the Lucas stuff had these pseudoprimes, these fakes coming in. He basically said, if he proved that if the row number is 2 to the power minus 1, a Mersenne number, and you start with the sequence 4, and you do the square minus 2, the 2 to the prime minus 1, 2 to the p minus 1 is prime if and only if it divides the Lucas number. So here's a case where so let's look at that. What do you mean by this? Well, again, his test is this. The Lucas-Lamer test is say start with 4, square the previous term, subtract 2, divide by the number you're testing, take the remainder. Do that until you calculate u sub p, and if it's 0, you have a prime. If it's not, you don't, and it's definitive, right? There's no pseudo primes or fakes coming in here. So, for example, if we're going to test if 2 to the 5th minus 1 is prime, it is, but we'll test it. It's prime if and only if the 5th term is 0 mod the number you're testing. So we start with 4 by definition. We square it, subtract 2, divide by the number we're testing, 31, and get a remainder of 14. 14 squared minus 2, divide by 31, we get a remainder of 8. 8 squared minus 2 is 62, divided by 31 is 0. And because it's 0, we know that 2 to the 5th minus 1 is prime. There's also the case for 2 to the 11th where you don't get a 0. So it's definitive both ways. And in fact, that was what I used, that particular method I used in 1978 and 1979, just only a couple of years before your GOS group started having meetings. And using a CDC 7174 by Seymour Cray's design, and found two Mersenne primes. Now, the Mersenne primes have a couple of problems, and one is what I call where you hit the exponent wall. So let's think about what do you have to do, right? You need to start with a number 4, and you're going to square or subtract 2 mod. And when you square a p-bit number, you'll get 2p bits long. So you're dealing with numbers that are twice the exponent length, and you're doing that p times. So you got to square, subtract 2, and mod. Well, squaring required typical type of thing you do a pencil and paper method. If you get a 3-digit multiply, you're going to get basically 3 squared products, 3 squared adds, if you do it in the classical way. And that's a thing. Now, subtract 2 is trivial. That's very fast. That divide by the number and get a remainder, there's a trick, and that is you can do a shift and add. So here's a case where we're in the process of testing if 2 to the 31st minus 1 is prime. So our p is 31. And we have this intermediate number of this squared minus 2. What you do is you peel off the bottom 31 bits, because you're testing 2 to the 31st minus 1, add them together. If you get a carry, you just wrap that around, and that's it. That is, to divide by a number and get its remainder of the form mod 2 to the p minus 1 requires really a shift and an add. It actually turns out to be very fast. So in calculating use of x, you need a square, and that's, square is required, basically O of p squared. Subtract 2 is trivial. The mod, the remainder, turns out to be just a shift and add. So, and you got to do it, you got to compute use of p. So what you're doing, you have something that's complexity, we call it complexity, of p cubed. What does that mean? Well, let's say it takes you 1 day to test some 2 to the p minus 1. If you want to test a number that's twice that exponent, it'll take you 8 days. 5 times the exponent will take you 4 months. 10 times the exponent will take you 2.7 years if the m sub p takes you a day. This is the exponent wall you run into when your exponent starts going off the table. Now, there's something you can do. One of the things is you can pre-screen, right? If these Mersenne prime tests are complicated, well, if you can show the number is not prime, you don't need to test it. And it turns out, a rule of thumb, with various properties of these Mersenne numbers, you can eliminate about half of them. So you say, if this number is not prime, we don't need to test it. That gives you a little bit of breathing room. But it comes down to how fast can you square. Again, remember, we start with 4, square minus 2, mod the number we're testing, which is a shift and add. So it comes down to that, how fast can you square a large number? And by the way, you have to square all the bits. You can't just floating point round. And so one thing you can do is you can increase the base. You don't have to do it in decimal digits. You can use the computer's word size. So if your computer if you have a 64-bit processor that gives you a 128-bit product, and you get a 120-bit product divided by a 64-bit number to give you a 64-bit division remainder, and you can add, subtract two 64-bit numbers, you can do it based to the 64, and that gives you fewer digits. Even though it still is O of digit squared, it gives you a little bit of a boost, but it's only kind of a temporary boost. The real way, the modern way to square large numbers rapidly is by using transforms. People have probably heard of Fourier transforms or discrete Fourier transforms. Well, there's a thing called a convolution theorem if you go in real analysis, and it says essentially that the transform ordinary product equals dot product of the transforms. What do you mean, so what? Well, it means if you're going to multiply two numbers, what you do is you transform the two numbers, you do a dot product. Now, dot product is not that cross thing in multiplication where everything gets multiplied, everything. It's just pairwise on an array of adding together. So we're basically only adding the pairs together, and we inverse transform. That turns out to be d log d operations, better than d squared. Now you might say, and so what do you have to do? Again, to transform, to remember in Lucas stuff, we have to square these numbers. We just transfer the number. We squared individual elements, and we inverse transform. And what you get is as if you did the multiply without any carries. So you have to propagate the carries to do some normalization, but that's a fast thing to do. But the main thing is it's much, much faster. So can they take that same case where it took you a day to test 2 to the p minus 1? Um, Twice the exponent will take you 2.7 days rather than 8. At 5 times exponent, it'll take you only 40 days rather than 4 months. And instead of, for 10, instead of 2.7 years, you're at 7.6 months. So it gets better, right? Now, it turns out you might say, well, wait a minute, you just said transform an integer? What kind of transforms are Fourier series and infinite cycles and so forth? What kind of lunacy you're talking about of transforming an integer? Well, um, the fast and loose thing is this: treat the integer. If you want to say how are you doing all these waveforms? Well, let's treat the integer as if it's a waveform, square waveform, and assume that that waveform is infinitely repeating. When we talk about transforming, we're asking in this infinitely repeating cycle, what are the frequencies? What's the frequencies involved? It's really what's going on. And and then when we inverse transform after doing all the product stuff, on dot product stuff, you just sort of, you in DFT, you get approximations because it takes too long to do an infinite series. You sort of cut it off at some point. You'll get some rounding errors, but you round it, and that
Dr.
is
Spitzmiller, am I audible?
yeah. I don't know if we are back.
You are back.
Okay. Um, I apologize. Let me go back here. I don't know what happened with stuff. I need to go back to, I need to go back because something interrupted us. So let's go back to here and return. I apologize. I'm not sure what there's. So again, we're talking about transforming, and I was talking about it grows nicely. What we think about the integer as a wave that's infinitely repeating, and we're looking at a spectrum. And I'll mention that when you multiply a pair of p-bit numbers, you'll get a 2p product. So what you need to do is to have a transform that's twice as big. You basically need to pad it with leading zeros before you multiply because you want to get the full precision out. So you need to basically have a 2n bit equivalent of a transform. And so how do we square a p-bit value? Well, we pad it with p leading bits. And the transform might have certain size requirements. You got to scale it for that sort of thing. You transform, you square it, you inverse transform, and you end up having to do normalization and propagate the carries. It's a fairly straightforward process that really does work. So here's an example. I'm using example. I did a decimal thing of we got 32. So we need two leading bits, two leading zeros there to pad it out so we get the full precision. And so when we do a transform, we get some complex values that we square those terms. Inverse transform, we round to the nearest integer, extract the reals. We get what would be the case if you did a multiply without any carries. So we propagate the carry and we get 1024. It really does work. And I won't go there, but there's examples of code showing you how you load your number into the complex array, do a forward transform, square the elements, inverse transform, do your normalization, propagate your carriers, and you're done. And it really does work. Now the details are in the rounding. Obviously, you can't just have a 1-point transform. You don't have the precision. You need a number of points to vision. And because you do rounding and other things, you're approximating the sines and cosines. You can't use full precision. So the Amdahl group was using an Amdahl vector processor, an IBM mainframe style machine, had a nice 6-bit mantis in its floating point. We could only use precision up to 23 bits because of rounding stuff. But you have a number of things, give you a number of points. So we were doing stuff at 18,900 point transforms at base 223, and it worked out quite well. No, there are better things than the standard discrete Fourier transform. There are number theoretic transforms. I mentioned a couple here. There's a whole primer on these things. There's some really nice code out there. Some of them use integers. If your hardware does faster in integers, some do single precision floating point. You can pick and choose, or you can develop your own. All it has to do is to satisfy the convolution theorem. So, what does it take to do a merge send? Well, really, you're going to start with a table of candidates, of powers. You look for small factors and toss out ones you find small factors of. And for each thing remaining, you start with 4, and you're going to pad it with leading zeros, do a transform, square each point, inverse transform, and you propagate a carry. So that's your square. Subtract 2, and you do the mod by shift and add. You do that p times, and if you get 0, you celebrate. Otherwise, you try again. And by the way, there is the AFF has a cooperative computing awards where the awards are given out to people who are the first to prove a primality of a certain size. The first two have been plain, but if you the first entity to prove a number of 100 million decimal digits or more gets $150,000, and for the first billion decimal digit prime that's proven, you get $250,000. Now, I have to be, disclosure, I'm on the committee and I helped actually set up this award. We set up this award to be exponentially harder. So even though you're adding decimal digits, this is getting substantially harder. Even if you're using transforms, you're still hitting an exponent wall, and these are fairly formidable in scale. The last one was 2009, and we're still at 2026 with unclaiming on there. Getting closer, but it's very difficult to get there. And by the way, you just can't say, oh, this number is prime. You have to actually publish a proof in a refereed mathematical journal, and then we'll look at it and see if we accept the proof or not. So you can look up the rules on how to do it. But there's out there awards for those people that achieve these milestones. But it turns out that while the Lucas-Lehmer test is the most efficient prime modality known, again, the effort versus the size, it's not the fastest way to find a new largest known prime. The reason why is Mersenne primes are rare. They're very rare. Only 47 out of the first 43 million some odd Mersenne numbers are prime. And they're getting rarer, right? If you look at the Mersenne numbers that are between 1 million decimal digits and 20 million digits, there's only 4 out of those nearly 2 million that are prime, and they're getting rarer and rarer and rarer. And we still have this p squared log p exponent wall you're running into. The last we knew where we could get a good analysis of how long it took. The one record in 2018 took 6 days of a machine that was fairly well tuned to the Lucas-Lehmer test in order to prove its prime. So it's getting harder and harder and harder. But there's a different way to do it. You can, instead of searching for 2 to the power minus 1, you're better off searching for a multiple of 2 to the power minus 1, h times 2 to the n minus 1, so-called Reisel numbers. This Reisel test is almost as efficient as Lucas-Lehmer. It's about 10% slower, but it has some very significant advantages. First of all, the testing of h times 2 to the n minus 1 grows as the exponent, not the multiplier. Now the multiplier has to be less than the 2 to the n. It needs to be odd, but instead of climbing the exponential wall as your exponent gets bigger and bigger, you can fix n and vary h. Another big advantage is that when h is reasonable in size, it is at least more than 2n, you can pre-screen sieve out non-primes at a much, much, much higher rate. Rather than 50% of the Mersenne numbers falling away by looking for small factors, you can eliminate more than 98.5% of the candidates. You can eliminate a lot of your work by casting out numbers that are obviously not prime. Finally, the numbers h times 2 to the n, where h is greater than 2n, are not rare like Mersennes. They're as common as normal primes. And you can actually calculate the odds based on number theorem on guesstimate actually how long it's going to take you to find one given the odds that are there. So again, it's almost as efficient. You can vary the multiplier and keep the exponent so you don't climb an exponential wall. You can eliminate nearly all of your candidates, and they're not rare. So all really good advantages. And we dethroned the Mersennes back in 1989 on sixth group. This is the number we did there. It was only 37 digits larger than the previous prime. We didn't use a Lucas-Lehmer test. We used a Reisel test, and we squared using transforms. The Amdahl machine at that time had a very efficient probability testing. We were able to test a thousand digit. We were able to do a thousand digit test at a rate of about once every 6 seconds. So it used to be that they kept a list of all proven primes greater than 1,000 digits, and we just flooded the thing such that you have to have a much larger prime in order to get onto the top primes list. So I mentioned, say, the test is Lucas-Lehmer-like. So what do you do? Well, this number is prime if only if, first of all, your multiplier, has to be odd and less than 2 to the n. Your number can't be divisible by 3. And what you do is you say it's prime if only if you get a 0 by doing this Lucas-Lehmer-like thing. You start with a u sub 2, not with 4, but with perhaps a different value, but you're still squaring minus 2 mod. So you still have some selection criteria. You start with some initial value and you square minus 2 mod. But again, you need to verify that the number is not multiple 3, but you're checking for small primes anyway. The exponent here is in. It doesn't have to be a power. It doesn't have to be a prime. You can do h times 2 to the billion minus 1. The exponent in front doesn't have to be prime. We can actually calculate. You have to calculate mod h times 2 to the n, not 2 to the n. And your initial u sub 2 value depends on something called v sub h, not always 4. So what do you mean? Well, again, you can pretest. You can figure out whether h times 2 to the n minus 1 is not a multiply of 3. There's some stuff depending on whether n is even or odd as to whether or not h is leaves a remainder of 1 or 2 mod 3. You can test only odd h's anyway, because if it's even, like 6 times 2 to the n minus 1, you just take the 2 and put it in the exponent and say 3 times 2 to the n plus 1 minus 1. And again, we recommend testing h between 2n and 16n so that the numbers are as common as normal primes, but the multiplier is not too big. So I mentioned it's Lucas-Lehmer-like. Instead of starting with 4, you got to figure out your starting point. Well, if your multiplier is not a multiple of 3, then you use this v sequence. It's kind of a Lucas-like sequence, and you compute v sub h. And if the number is a multiple of 3, you do this thing with the similar thing with this Jacobi symbol, another sequence of computing v sub h, where h is again your multiplier, but you're using a Jacobi symbol. And Jacobi symbol is not that bad. It's just this algorithm for looking at the bottom bits and doing some flicking around, but it's a fairly fast thing to do for this precondition. Now, how you find v sub 1, your starting point. Remember, you have to start with v sub 1 to get u sub 2, and then you can do your square mod 2. So you start with, you get this, what you can do is you can start with one of these primes, perform this Jacobi test, and if it passes, do the sequence to start off with your u sub 2 and carry forward. It's a fairly good thing. This set of numbers, fewer than 1 in a million cases fall through. There's a way you can really test it if you wanted to do everything. If it's one of those rare cases, you could just try another one. It's fairly easy to do. So again, how to find your starting point, v sub 1 to get your u sub 2. If it's not a multiple of 3, you can either try a 3 or 4. And if it's a multiple of 3, you go through the sequence. So example, remember we did the Mersenne test of 2 to the 5 minus 1. Well, 7 times 2 to the 5 minus 1 can be tested as follows. First of all, we have to figure out what is our u sub 2. So because 7 is not a multiple of 3, we start with this 2, 3 sequence. You go through this sequence of figuring out what your v sub 7 is. V sub 7 is your u sub 2. So there's your u sub 2. Not instead of 4, it's 174. You're modding by modding by the number, squaring minus 2, modding number. So it's the same kind of Lucas stuff. You're squaring a minus 2 mod, And if you get zero, it's prime. If it's not, you try again. Now, this finding use of two as well, again, it's an easy thing to do. You can use calc to generate the number to get your starting points. It's just a tiny bit of work, bookkeeping, to figure out what your starting position is, because it's not four, it tends to be a different number. Now I mentioned, okay, so we got this starting sequence. We're doing squaring by transforms. Subtracting 2 is easy. How to do this mod h times 2 to the n minus 1? It's not just a simple shift and add. It's a little bit more. You have to do this you got this division by h and mod h, which is a little bit more work. That's where the extra 10% is, but it's not much. And so it's just a matter of peeling off the bottom k bits, keep putting these two values and slime them together, and you're done. So you don't have to do a lot of calculation. It's just a tiny bit more. And again, computing requires you to, for 2 to the minus 1, you peel off the bottom k bits, you perform these calculations of dividing by h and mod h, add them together. If you've got a overflow, you just bring that back around, and you're done. So for this reason, with stuff, you want h to be small, like a single precision number, not some huge number, because you have to divide by it, and it's easier to divide by a single number, a single digit. But you want to be too small, because again, if h were 1, you're just 2 to the n minus 1. You're back to the Mersenne rarity. You want to have h be at least 2n, but not stays within your word size. On the pre-screening, the Reisel test candidates, you can avoid testing, obviously, things are not prime, by sieving. You might have heard the sieve Eratosthenes, where he said you throw away 1 because it's not a prime, but you take the next one that's remaining, 2, and you cross out every second one. You take the next one's remaining, that's 3, and cross out every third. Next one is 5, you cross every fifth. And you keep doing that. What you end up with, less than the square of the thing you've crossed out, are the primes. Now this sieving method, where you're marking out you find a prime and you mark out all its multiples, you don't have to start with 1. So here's a case where we start with 100. And all you have to do is you start with the first prime, 2, and you find the first number that's multiple 2, and you knock out every second one. And the first one that's multiple 3, and knock out every third one, 5, 7, and so forth down the line. Once you find your starting point, then you can just turn off all the rest jumping through, and eliminate many classes. You don't have to test each number. Once you find your starting point in your table of candidates, you can eliminate a whole class of these very, very fast. It turns out you don't have to go stick with integers. For example, there's no point in having even numbers in your list because they're all even. So if you just took the odds, that still works. Every third odd number, every fifth odd number, every seventh odd number, when you find the starting point, works. In fact, any arithmetic sequence. So we're testing h times 2 to the n minus 1. We look at all of the h to the n minus 1 for some table, and we find the first ones, the multiple 3, and knock out that stuff. Remember, you have to also do that on the test. You find the first ones, multiple 5, cancel it, and knock out every fifth value. So once you do the 1 division, your entire table gets rid of all the multiples. And again, you can do some sieving and there. Now, how far do you sieve? How deep do you sieve? I mean, one thing says, if you're sieving numbers and they're falling out at a faster rate than you can test, you should be doing some sieving. But if you only sieve, you're not going to find a prime. So really what you want to do is you want to start testing Reisel numbers, do the computation while you're sieving. And as you start knocking out candidates, you want to look at the rate you're knocking out candidates, and once your rate of knocking out candidates while you're testing approaches your speed of testing, then you no longer need to sieve. You've probably sieved quite enough. Now, finally, we've mentioned that these Mersenne tests, or the better Reisel test, really involves around how fast can you multiply, how fast can you do that square. And transforms are pretty good. They're n log n on an n-bit multiply, but they're not as fast as you can do. If you are hardware inclined, if you have ability to make chips and so forth, or there, you can build a device that multiplies and adds in linear time. What do you mean by that? Well, you can do an n-bit multiply and on top of that n-bit add at the same time in just two n clock cycles, two n steps. Now you have a bunch of state machines, but these are simple 11-bit state machines, and it calculates your multiply and your add. So you have for free your square and your minus two all in one step. To do an n-bit square minus two requires n over three state machines. The nice thing about this system is that when you input, you input your initial values, right? Your u sub two or your u sub n and your minus two. You're inputting those, and you're getting out at the same time your results. So when you input and clock 5, your fifth input bit, clock 6 gives you your fifth output. So as you keep feeding it bits, you're getting the answers back one step later, and you're doing it in linear time. Now, state machines are very simple. They're 11 bits. They have these values here. The first one is special. That's your input, right? They're feeding your input in, and your answers come out on that same state machine. The state machine as well is a nice linear array. You don't have some giant crossbar thing you have to do. The state machines are just talking to the left and right neighbor. That's all. You don't have to pass lots of bits around on a mesh. You're feeding a couple of bits to the left and receiving one for the right, and they're just all doing the same thing. What do they do? Well, it depends upon that one of the values C, and it turns out that all but the leading three have this or stay in this state of C equals 3, and they do this calculation. This calculation, these variables you see are single bits, and the AND is an AND gate or AND gate. So we have here 4 AND gates, and then the add is a 3-bit adder. So basically, you have to go through 4 AND gates and do a 3-bit adder, and that's it. And then you pass pass 4 to the left and get 1 from the right, and you're done. Very, very trivial, simple state machine that's running. Now, you're going to run this, for example, I did calculations running at 25 gigahertz, and so that's 40 nanoseconds 40 picoseconds, and that's pretty good. Remember, because you have local memory, 11 bits of local memory, and you're going through 4 AND gates and a 3-bit adder. Easy to do that in 40 picoseconds. Even you can do it even much faster if you're clever in your hardware. But only at 25 gigahertz, you're already as fast as the Mersenne are doing in their, for example, at the previous record, right? And remember, you are growing at O of your products are O of n, not O of n log n. Moreover, because you're not climbing the exponent wall with Reisel numbers, you can have a whole bunch of chips running in parallel where all your state machines for a single test is on one chip. You have a bunch of chips running in parallel, all testing different Reisel numbers that you've sieved out, and you'll get with multiple chips, you'll be much more competitive than the thousands of flocks of PCs out there. Now, a couple of words of encouragement. Final words. Results and records go to the first to calculate correctly. It's not necessarily the fastest tester. It's the first to do a correct proof. As Dave Lamer said, a slow correct answer is infinitely better than a fast wrong answer. If you're going to join wrong answers, just say 4 and be done with it. You don't have to. So you need to do it correctly. You need to compute smarter. You don't have to have the fastest machine. You just have to have correct machines with good quality control and good testing. My eight world records relating to prime numbers, I never had the fastest machine. I usually had something that was 2 to 3 generations behind the state of the art. So I recommend avoiding premature optimization. Write your comments first, write code that works with test cases, start the test running, continue to optimize. And when you find one that a little bit faster and it passes your test, put that into play, right? So you can begin to get going and get it faster and faster and faster as you go on. Another thing I would say is test, test, and test. Don't trust that the hardware is going to work. Don't trust that the software is going to work. Have lots of checksums and sanity checks in there. Check your memory. Do checkpoints along the way, and if you find an error, restart. Also remember, you need when you do a probability test, you probably want to confirm your test. It'd be a shame if you had a bit flip and it was the prime, but you missed it. So what you should do is double test everything and check your results. If you get the same end number, the same use of P out the other side, you have a pretty good idea that it's working, or at least you're getting consistent values. Most CPU cycles are not spent as primarily testing. You'll probably spend about a third sieving, limiting candidates. Expect these primary tests to be done twice. So you test it and some other piece of hardware, equivalent hardware machine, you test it again and compare the results. So only about a quarter of your cycles will actually, and quarter of cycles will probably involve error checking and testing and intermediate values along the way. So, and of course, you must verify and then have someone else, you probably want someone else to go in and check as well. So you've got to do 3 tests. So really, it's a matter of saying that probably in about a quarter of your cycles are going to go towards forward advancement. But again, a slow correct answer is infinitely preferable to a fast incorrect answer. Now, how do you find an large known prime? Well, here's the, if we got the 2 to the power minus 1 as the being largest known prime, we'll pick an n, because remember, the Lorenzo test doesn't have to be prime, just a little bit larger. And I mentioned this in how you do the sieving, but you'd like an exponent with as few 1 bits as possible. So here's a value of n just a little bit bigger than the record prime. Your h is going to be between 2 and 16 times that n. You're going to sieve to eliminate all the candidates. The ones left, you start with your v sub h, compute your v sub h, and pre-compute those ahead of time, You're doing your square mod stuff using your transforms or your hardware. And you do that in parallel, and the first time you get 0, you can go and celebrate as finding a new largest known prime. Now, the odds of testing a number like this, they're rare, but they're not as rare as the Mersenne. Here showing the calculation, you need to do about 2.8 million tests. But look at this graph. This graph shows you from the first digital computers, these Mersenne prime tests, where the y-axis is the number of digits, and that's in log, and x-axis is years. And you notice that the Mersennes are flattening out, right? They still haven't hit that 100 million thing. You get the next Quantum Computing Award, but they're running into problems. They're flattening out. There's some reasons I can go into as why that's happening in the Mersennes. But all you need to do is to go a little bit higher, go sideways, so you keep in vary h, sieve, do your either hardware or your transform multiplies. You could do it in parallel, and on average, if you do about 2.8 million, you are almost certain to find a new largest known prime. So could one of you right now, or a team of you in that thing, find the largest prime? Absolutely yes. If you focus on correctness of computing, you focus on error detection correction, don't blindly trust stuff, hardware, firmware, drivers, compilers, do testing, checking, so forth. Hardware people consider that fast multiply add circuit. Build a team of people with complementary skills, and you're going to, I think, have a really good opportunity. Now, it takes time. Don't get discouraged. As Lamer used to say, Havana to say, happiness is just around the corner. Now, you happen to be searching a many-sided polygon building, but you just have to find the right corner, but happiness is around the corner. So use complementary strengths, have team members check each other's code. If you use outside code, always start with the source code and study the code and check for correctness and put it build-in tests and so forth. But if you do that, run in parallel, and given you know how rare the Reisel numbers are of that class, you can estimate your progress. Now, you could have the first test come out prime. That's probably not going to happen, but you test some number and you're almost certain to find it. So could one of you find a new Logos prime? Definitely yes. And definitely now that the Mersenne are running into this severe exponent wall, you can sidestep like we did with the Amdahl group, just a little bit higher, launch this stuff, especially if you're doing the hardware, you can run this stuff in crazy parallel. You can put on a chip the entire MERS Reisel test on one chip and have those things run in parallel and beat tens of thousands of PCs out there quite easily because you compute smarter rather than harder. Now, there's a bunch of resources out there. I list there. You can see on the screen of how to do some of the stuff with circuits and transforms and so forth. Think about the right test. Put a lot of stuff there. Of course, I'm available for asking for advice on things because I certainly like to see somebody regain stuff there. But at this point, I say, that we reached the bottom of the talk. Again, this is something you can do. I think there's people in the room who could team together and do it. I think right now, the current state of affairs, just like we did in Amdahl, they hit an exponential wall and you can sidestep it and do much more efficient. So with that, um, we have time for questions
All right. Thanks,
and maybe
Landon.
answers too.
Yay! Thunderous applause from the audience here and from the folks that are online that are still hanging in there with us. We're going to open the floor to questions. The folks on Zoom, you'll have to unmute yourself
Thank
in
you,
order
Anna.
to ask, or raise your hand, or
Landon,
And
can
I'll
you
let
hear me?
you, Dennis, moderate
let,
that. But
let,
again,
let me go to Daniel right now.
Am I audible? Can you hear me?
We
yes, I
can hear
can,
you,
Daniel.
Daniel.
Excellent. Great presentation, Landon. I have a
Thank you.
question about it was concerning to me, the reliability that you found. You're doing these long, very, uh, where accuracy is critical. And then we were finding computer errors. And I wonder, we use computers in safety critical systems. And I am sort of concerned based on the errors that you are countering in your long runs, that maybe the safety critical systems are not quite so safe. So do you think maybe it doesn't make any economic sense, but there's error checking and correcting memories and maybe even dual processor systems running in lockstep, and they should have exactly the same answer at all times. So at least they'd be able to spot an error. Assumption being that there's no systematic error, that this is one of those
Sure.
random things. How do you see any path to improving that error rate to get it much closer to zero?
Well, yes, I mean, that's a very good point. And again, with critical systems, hardware and software has errors and bugs and faults, and more hardware and software has even more faults. So rather than have something to try to perfection, assume there's going to be problems and correct. Um, and those that you can't correct, you can at least detect. Because the worst thing to do is to have a result and not know you've been had. We in these one of the things about this problem of testing is that it has to be exact down to the last bit. It's a really good hardware checker. It's one of the reasons why Cray used it. All the Crays ran in their idle loop, Mersenne prime checking because it was a really good way to check faults. You can begin to characterize hardware. So when I worked for companies that had hardware stuff, we ran primarily testing in the background to actually characterize some of these things and identify problems. Um, you find that you build in techniques to begin to do these, to become fault resilient, not just perfection, but fault resilient, and detecting these faults and rolling back and restarting is probably the best thing to do. And any critical systems, if you're doing a spacecraft on outer space or flying an airplane, things will go wrong. You build in lots of checks and steps to try to mitigate where possible. Now, can you do perfect? No, but in the case of mathematics, you can build a proof that will survive peer review and will be replicated by somebody else. So that's how we can trust the result there. But you raise a very good point. And a lot of the techniques that you develop in doing this stuff, like again, the length of the calculation you're going to do is longer than the mean time to error. And you'll find, for example, when I had my study as students do some checking back model in 2018, we found that a typical Intel processor would make a calculation error that like add 2 and 2 and get 5 at a rate about 1 in 10 to the 15th cycles. And if you figure, well, you're at a gigahertz, that's 10 to the ninth, and you have 10 to the seventh seconds, and if you have pi times 10 to within in seconds, pi times a million seconds in a year, you're having an error about every 30 or 40 days. You can have software to catch that and correct, but you have to do that. When you get to GPUs have a much higher error rate than CPUs. We saw a typical NVIDIA CPU compared with the Intel processor stuff, that the error rates at NVIDIA CPU were around 1 in 10 to the 10th, like 5 orders of magnitude worse. And if you overclock your processors, you're going to run into errors much faster. If you try to buy the fastest processor you can, the bleeding edge processor, you're going to find much more errors than if you rolled back and said, I'm going to take something that's a little bit slower than the new bleeding edge. We even found that we could tell when someone left the machine room door open and letting all the cold air pour out and hot air pour in, because we can start to see the error rates that we're catching go up. And we see the error rates and say, hey, somebody left the door open, close it, and return back to our normal error rates. So there's a lot of value in this kind of exercise. I would think for students and so forth, or if you have a critical system, going through this exercise will train you to write code. Because here's the thing, I say, Daniel, this calculation is so long, you don't really have the opportunity to do it again. You're testing, but you don't have time to run it again. It has to work correctly the first time. When you approach it that way, you have a discipline that can produce really solid results. And I found with that same discipline with other critical systems I was involved with, that they could be fault resilient. And again, it's not the fastest, it's the first to do it correctly. And really it's going to come down to how good is your QA? How good is your fault detection? How good is your fault mitigation and correction? And yes, you do things like you say, hey, I paged into memory. Let me put a tag into my page and check that I got the right memory, because maybe the memory management gave you the wrong page, right? You can check things like that, and you'll find errors. We had, the IBM thought that the IBM mainframe was bulletproof, and we found bugs in the IBM mainframe. We found bugs in the compiler, right? That it produced assembly code that wasn't quite correct, and the code would catch that because the calculations are unforgiving. It has to be correct to the last bit. So there's value in these critical systems you talk about, the disciplines you do to get there, is there. Again, you start off with code that's slow and buggy and failing tests, and you visually improve things. Having multiple people on your team is really good at checking stuff, and eventually you'll get something which will be able to exceed the normal mean time of error of a single thing, and with enough effort, enough parallel stuff, you'll get a record, and you'll learn how to write code that works correctly.
Thanks. And one more last thing is, if I wanted to learn to be a better error checker program, in other words, be able to write programs that check themselves more efficiently and correctly for correct operation, what do I research? What do I need to learn to make that happen?
Well, probably the first thing is to assume it's not correct, right? Assume that it doesn't. Don't assume when you add two variables that you get the sum, right? You write code, and so maybe what you want to do is you want to have, you say, well, have two variables, one's complement of the other, and add twice. Maybe you have a processor that has a pipeline with multiple adders, and you run through stuff. I mean, one of the reasons why, for example, like the IBM mainframes had such a really good, long mean time to failure, mean time to error, was their ALUs actually had three things running in parallel. They ran the calculations in three different paths and did a vote. And if they found that two outvoted the third, that's the result they went with. If they had three different values, then it did a processor fault. And back in the 1990s, they had failure rates at around like 50,000 hours MTBF because they did things like that. But the first thing is you don't assume that your stuff you have is working. Don't assume the C compiler gives you the right assembly code. Check the assembly code. Don't assume the processor is going to calculate correctly. Don't assume that the firmware is correct. Don't assume. So you say, well, if I don't assume, if I can't trust it, what do I do? Well, you verify. And you start building in these tests to verify. You try to figure out like, okay, I have these two values, but maybe I can do the product mod 7 and see if I catch that. Or maybe I have values where I can check if bits flip. I can do CRC checking. There's a number of things you can begin to do testing on. It's hard to say what errors you run into because it can depend on your hardware. But the first thing is to assume you will have errors every place. The operating system, the firmware, the chip bugs, right? Remember, Intel has never commercially sold a processor for which you could not take a set of non-oblivious instructions and compromise the system. They've never been able to do it. All of them have bugs, but you can check your results and counter-check results, do like the equivalent of like nines checks and so forth in there to begin to check things. You can do double testing, you can do parallel testing and independent hardware and begin to see these things. And you'll begin to see the faults. I know that, for example, BSD had a lot of resiliency into their kernel because we were running these things on BSD kernels and we started finding faults there. It turns out they had a memory smash thing that could cause them to page the wrong page in from swap. So you can begin by assuming the stuff you're using as bugs and accept that and then say, okay, therefore, how do we go about checking it? And you measure the stuff. You will, at the end, characterize your failure rates very well. You will understand how often a disk drive gives you the wrong value, how often bits flip, how often CPUs, and you begin to look at the things and compare stuff about saying, hey, overclocking may give you a couple % faster, but your error rates go off the wazoo, so maybe consider underclocking. But on the other hand, example of processors, there's a lot of processors that have this notion where you can vary your CPU cycle. If it's not doing anything, you can lower the CPU cycle down. And that varying of cycle rates of a processor is deadly to errors, right? When the processor changes its clock rate to try to do some power management, you get all kinds of really bad errors. So when you detect these errors, you then try to figure out what went wrong, how to detect it, how to correct it. Again, and you will benefit from this and other processes, being able to write stuff that works correctly, or you
Thanks.
have the trust that it's correct.
Thank you very much,
We have
Landon.
a question here in the room.
Sure.
Landon, are you familiar with Carmichael numbers?
Yes.
Do they have anything to do with primality testing?
Well, yes, I mean the Carmichael numbers, h times 10 to the minus 1. The Reisel tests are the tests for the -1 case of the Carmichael numbers. There's a similar test for the +1 case, h times 2 to the n plus 1. Those have a little bit different properties, but definitely Carmichael numbers, there's a lot of benefit from that. We certainly benefited from Reisel and so forth, who did a lot of work in testing those Carmichael numbers. And again, that Reisel test is an h times 2 to the n minus 1, which is one of the important subclasses of Carmichael numbers. Now, it turns out the Reisel test requires your multiplier to be less than 2 to the n. So there are Carmichael numbers that it can't test, but if your 2 to the n is huge, having an extreme h is not very helpful anyway. But yes, it's very definitely related to Carmichael numbers.
Perfect.
And
Thank you.
good question.
Other questions?
So again, the having somebody in your team who really understands QA and has a passion for QA, and is checking your code and having things in runtime and having things done in testing in parallel, so forth, is going to give you really good things. And so I can tell you that, I've worked on deep space probes where you can't go out to the space probe and reboot it. You've got to deal with it remotely. You build in all the sensors, you build in all the methods, logging lots of stuff and having stuff check the log, having stuff check the checks, right? Because we found often that the bugs we had was in our testing, not in the things we're testing, right? It tends to be we tend to fail on the testing side, testing code, than the code we were testing. Now, transit errors are also there, but as I say, when it has to work correctly the first time, and essentially this is something it's too long to run twice. So your processes of all this checking has to work correctly the first time. You will build a discipline that will be quite beneficial in writing code that works. That was the thing when I retired, my executive director said that I had a passion for things. I wanted products to work. He said that was a unique passion I had, which I thought was a little bit disappointing because I would think in engineers you would have a passion for, I want it to work. But again, assume it won't. And those things you can't prevent, you at least mitigate. You can't mitigate, at least detect. And at that point, you do it well, you are well beyond the stuff. And of course, yes, there may be one of these Reisel tests you've done. You let a Carmichael prime slip through, but you're testing a bunch of things. You'll find another prime anyway, eventually, if you do it correctly.
So, Landon, you're basically throwing down the challenge for all of us to start making our own teams and come up with our own ways of working on this stuff. Yes?
Yes, absolutely. And that's where that's why we called it Cooperative Computing Award for the EFF. We wanted people to cooperate and to do these large calculations. That was part of the encouragement. Now that 100 million decimal digit thing is a formidable number to try to reach. That is, it's deceptively hard. That's exponentially hard. So I wouldn't try to go for the 100 million digit, plus
not today.
record. But sidestepping the largest known prime, going sideways, and if they find another one, you just retool and jump up to the next thing just beyond it, do sideways, you'll get it there. And you end up also being a very good connoisseur of hardware. You end up looking at memory manufacturers, DEM chips, or if you're doing your own circuits, as to who does a better process for things. You might ask, would a 3 nanometer state machine be more error tolerant than a 5 nanometer, maybe backing off and not trying to do bleeding edge will give you a better process thing than try to eke out that last percent.
All right. And there's lots of resources there on your slides. I know your slide deck, the PDF that you sent is pretty big. It's got a lot more inside baseball. Yes.
Yeah. So I saw it, and there was a question that came in.
There's a question here. Hold on. Go ahead.
Someone.
Oh, I'll get him in a minute.
In a chat.
Landon, it's me, the Carmichael guy again.
Oh, yeah, sure.
I have a question. Have you done any estimation or recording of energy usage of these calculations for each prime and looked at how it's scaled?
Yes. In particular, we looked at, for example, things like does the GPUs give you a better energy density than CPUs? And generally, we find the answer is the CPUs because of they're actually better calculator than the GPUs. Gives you a better thing. Also, there's a lot of these transforms that are integer based. Some of those number theory transforms are integer based that floating point GPUs don't give you an advantage of, but the power that they consume is significant. That state machine is a really low power thing because you're dealing with 75 million state machines that have 11 bits and no crossings. So the actual energy it requires is much less than in a CPU. So energy wise, and again, that power and cooling is going to be a major factor in your error checking. You'll find that temperature and cooling are going to be really formidable factors in your ability to calculate correctly. So low power stuff with efficient cooling is a key there. High power stuff tends to have more thermal drift. Another thing you'll find is you've ever had a thermal event, such as your cooling in your data center has failed and your processors have been cooked. You'll find your error rate goes through the roof because you've basically built in a lot of failure into the stuff. So keeping your processors cool from the beginning and keeping them power efficient from the beginning is going to be key. Avoiding basically things that it's like avoiding a car that's been in a flood. Once you've weathered a car, it's going to have various interesting problems that is going to be a bane to a correctly working system. I don't know if that fully answers your question, but it is. But power and power efficiency is important. And if you are doing like that hardware thing with those chips in there, the power budget is something you need to consider, as well as cooling and efficient cooling. So you build a system that has an efficient cooling thing. I remember at Cisco in our supercomputer, we had an executive director who was really big in aesthetics, and I translated into the airflow through the rack needs to be unimpaired. I did not allow a rat's nest of cables to be behind the thing. I wanted the airflow to be efficient and not being choked by a bunch of poorly designed, poorly dressed wires. And you might think, how is that done? But that impacted the efficiency of the cooling, which impacted the error rate. And by getting the cables nicely dressed and the airflow being nice and laminar, it required less power, but also gave us a better error rate. So there's lots of advantages all
Landon,
along.
there are a couple of questions
Sure.
on the chat that
Okay.
I hope you address. One of them, Terry Bollinger asks, what surprised you most as you developed your methods?
I think one of the things probably that shocked me the most was just how poor a GPU calculation was in calculating.
Yeah.
And when you link the GPUs together, when you try to get these things that are even more beefier GPUs, the linkage drove the error rate down an order of magnitude. I think another thing that was there was just um, how many errors there still is. I think probably the shock was that when we found in the IBM, according to IBM POO, the principles of operation on an IBM mainframe, which was considered the bulletproof architecture, we found a bug that required mainframes to be fixed. Why? Because we had calculations that could detect the bug. Um, it certainly opened me up to compiler bugs that would compile and produce bogus assembly because why? Because we check the assembly and not assume the compiler is compiling correctly. Um, and so those are things I thought I was get so surprised that that stuff that you assume worked that actually had again, hardware errors. You would think a compiler would be able to do it, but I can tell you from the C contest and our sophisticated C contests that are run, one's running right now, we still get submissions that cause a C compiler to dump core. Valid C
Valid C. Yeah.
that causes a C compiler to crash. What does that tell you about C compilers, right?
Yeah.
Um,
It's
so
witchcraft, not science.
Yeah, so it's trust but verify, right? And efficiency, in time, in power, in cooling, and use are also key in getting stuff to work correctly. And again, these methods. So I think probably the some of the things you thought were the most bulletproof ended up having holes in them, was probably a surprising thing.
So there's another question. Sharma says, how long do you think it will take until another largest prime is found?
Well,
I think it would be kind of, who knows?
I would suggest that let's say that somebody's going to do the Reisel test, like the Amdahl 6 and sidestep, go a little above. I would suspect that it's going to be your development time for stuff. It might be like about a 2-year project for there, but it'll pay off quite quickly.
Hmm.
The Mersins have that exponential wall. One of the things that Mersins are running into is cache sizes are not getting that bigger, but the prime the Mersenne numbers are testing are getting bigger and bigger and bigger and bigger and bigger. And beyond that, the error rates in cache, like L1 cache, L2 cache errors, where you get the wrong thing out of the cache, is getting to be a problem.
Okay.
And so you're dealing with vectors that exceed stuff and saying, okay, I'll give you a 40 core processor rather than a 20 core processor. That doesn't help in part because putting piles of cores onto a chip tends to end up interfering with each other,
Yeah.
locking and other things happening as well as heat. So some of these things where you're going crazy multiprocessor stuff ends up hurting you if you want stuff to work. So I would say that the now tomorrow you can wake up and someone has a Mersin test as a new largest known prime, but notice that it took them a while to get that next thing, and it wasn't much of a step. Um, and the new one had a bunch of GPUs involved in it, so they got something to be able to do an error checking to get a correct value that was there. But I think it's going to be a little while. The for line for the 100 million decimal digit prime, if we had been going the way we did over the last some odd 70 years, should have been crossed by about 2022, and they didn't. Um,
Mm.
the Intel processors, the memory controllers are running into problems. These things are exceeding the capacity of these things, and so I think I think that probably the hardware thing, the hardware I would guess would be about an 18-month thing to get a foundry to create some wafers, but that once you start getting something there and you have your checking for your processors, that would give you a probably even faster route. But you can do it with software as well. You can do a lot of work with idle time on machines. Um,
Okay. Let me ask Daniel. He's got his hand up again with another question.
The
sure.
Go ahead,
one,
Daniel.
yes, I was very intrigued by your statement with regard to linking together the GPUs. And I know NVIDIA has this NV link that they use to link theirs. Now,
Yes.
Okay, so you laughed, and so I understood that made the error rate go down, is what I heard. I thought I heard you say. Does that mean that the error rate was
Oh,
better? There was less error, or did I
more
misunderstand?
error. It
Yeah.
made the error rate worse by an order of magnitude. So
Wow.
we
Okay,
had
thanks.
we had NVLink things that went from 1 in 10 to the 10th cycle errors to 1 in 10 to the ninth.
Thanks.
Um, and and one of the things that happened, so NVIDIA GPUs are really Silicon Graphics pixel pushers. Silicon Graphics was doing things like Terminator movies and Michael Jackson videos and that sort of thing, and had these engines that became the GPUs, the algorithms that were put into there. And one of the ways that they did this processing was they turned off a lot of internal error checking. In a modern CPU, they're doing checks inside the LU. And the same thing with mainframe, having these like triple checking of stuff. They cut off all of the things that you would have of the CRCs or things like that to try to get stuff going through. Um, the NVLink problem occurred because what when you send signals across a bus these days, it's not like an S100 bus where you just 101010. It's a whole bunch of frequencies that are between two ends where your SerDes are negotiating frequencies across the thing. And what NVLink does is they send out the packet and they cut it off. They don't let the packet trail off because you need the tails of those pulses to be correctly resolved in order to get the data block correctly. They're cutting off because they want to have back-to-back packets faster. Now, in the case of machine learning, um, you'll find that the GPUs are so bad that if you take a training from, you start with a state machine, right? Your weights and biases and your graph at a known set of values, and you pour your training data through systematically, you get the result, and you do it again. You go back to the original stuff and run it again. You will not, unless it's a trivial benchmark, get the same result. Your machine will be different.
They call that a feature.
And in fact, there are algorithms now. You're right. It's algorithms that do so. So people who build these NPUs, they're wise to put in a pseudo-random number generator to inject errors in if you have a really good calculator,
Reduces
because
the
that's a
hardware
feature,
cost.
not a bug. But that's making use of stuff. But yeah, it's the linking together because they want the packets to be back to back and with very little time between frames. You have patterns. There are bit patterns that can cause that wave train to be catastrophic in your error checking. And because they don't wait the full amount of time, you can get values there. So you're better off splitting, if you want accuracy out of a GPU blocks, not linking together, but treating them as individual cells, and then cooling the heck out of them, right? These giant boat anchor GPUs with stuff, that's telling you there's a lot of thermal errors. And when you cook them, when you have a little bit of a thermal shutdown, you have taken your transistor dopants and you've migrated there, and you'll find your error rates will become unfortunate once you bake them too much. So if I were doing a GPUs, I would cool the heck out of them. I would subclock them and over error cool just to try to improve the accuracy, assuming that you care about accuracy.
Ouch. Yes.
Thank you.
All right. One more here. Okay, go ahead.
Hello, Landon. It's the
Yes, sir.
Carmichael guy again.
Sure. Yes.
You briefly mentioned it, but I'm assuming you were referring to networking heterogeneous hardware. Can you talk a little bit about what protocol or protocols you're referring to in terms of efficiency of communication,
Yeah.
or just
So
point us
we're
to a good resource?
Well, there is, and I think there's research literature in how to do discrete Fourier transform (DFTs), in parallel across multiple machines, right? So if you want to have a calculation run in parallel and you want to do the FFT in parallel, um, the way you're doing the butterfly loop, your beginning stuff can stay on processor, but at some point your butterfly loop is going to span ahead of the processors. And so the result is you're going to need to have, if you're trying to do it, an interesting challenge is say, I want to have a single FFT run in parallel on more than one machine. And then I want to do it in a way where I don't have a fast bus, but I may have to do it over the internet, right? How would you end up designing a Fourier transform, DFT, obviously, because you're doing it, digital stuff, across the internet? And the answer is you probably have to batch these things up. You have to do some calculations and throw the packet across the network to take the other side. And so you have to sort of have some sort of thing where you have use the old vector technology things to have multiple packets in flight that you're running these calculations on. That's a thing. So when your calculation becomes too big for a single core, you have to enlist other cores. So you have to communicate. And that communication is going to be a challenge, especially once you go off chip to another chip and go off board to another board or go off processor to another processor. Every time you do those steps, not only there's errors and delays, but also challenges of the networking. The hardware wise, the hardware chip, you could still put enough of those nodes in a single chip that you don't have to go off chip, which is one of its disadvantages. But if you're going to try to do think about how would you do a multiply or an add spanned across several machines in your several PCs? How would you do the communication?
Yeah.
That's going to give you parallelism, right? Because you can now have a bunch of ALUs running on parallel, but that's going to have communication challenges that can overcome. But that's part of the thing is sometimes is because it's the state, the cycles, it states the cycles and the bytes per second you have to communicate between things that are going to tell you. It's called computational math, where you multiply the number of cycles times the size of your state machine, the size of your state, times the bytes per second you need to communicate across. And you'll find that you do better when that communication is balanced. You're not out of balance. You're not passively parallel, but anemic in data flowing through, or you're not huge memory, but too few cycles. You need to have a balance between those two. And communication is between, if you're doing stuff in parallel, however you do, you gotta get the signals back and forth. That communication, be it on chip, off processor, or across the internet, is going to be a challenge if you want to employ those methods.
We got one last question, Landon, and it's from our friend, Steve Fraser.
Hey, Steve.
He says, how might new computing paradigms influence the discovery process? For example, quantum computing.
Well, quantum computing remains a very interesting research, and I hope that they achieve some results. Right now, with quantum computing, the record quantum computing factorization is so small that you could think about it in your head and do the factoring in a couple of minutes, but they're getting there. There's promise there. I think quantum computing has some really interesting stuff with regards to how to do some of the multiplication, squaring. Squaring and quantum things can give you some really interesting results. Might be another hardware way. Again, it's exotic and it has its own problems. I think the other way that computing is done is the notion of true parallel processing, right? So code things like that things that do a Go or Rust, or they have some interesting multiprocessor paradigms, can give you some interesting stuff. They have their own issues, but the how to do true parallel coding and taking advantage of that parallelism is one of the paradigms I think that people need to consider, because individual cores, individual processors, individual nodes may not have enough oomph to do it. You have to distribute it, and distributed computation, multiprocessor computation is something. Now, there's a lot of literature out there that involves how to do interlocks, how to avoid deadlocks, how to do like database transactions across the world. There's a lot of research, and you can use that to learn about those techniques. You don't have to reinvent everything from scratch. There's a lot of good stuff out there on how to do that. And I think that's a paradigm that is there. Certainly storage and memory. There's always new sort of memory storage stuff you have to look at. One of the things is to characterize the error rates, right? So looking at new technology, if you have come along, do an effort to characterize how good is this, right? Because if you've got something that's claimed to be twice as fast, whatever fast means, but the error rates are off the chart, it's not going to give you a good mean time to correct answer. But I think there is technology. Quantum computing is out there. I predict that we'll have commercially successful fusion before we'll have quantum computers that are truly general purpose better. Not to say that they won't get there, but it's important. I think, on the other hand, some of the newer technology of how a disk drive, the new disk drives, the new memory systems, the new multi-core processors have interesting technology, and you can explore them. And one thing is to see how good they are and how fast.
Okay.
How fast they fail. So thanks again. Again, you can do it. It's definitely possible. If you want to get some further consulting, I'd be happy to help and give you some advice on things. It's definitely given right now where the Mersins are. It's just like we did in Omnidal 6. There's I wouldn't say a plumb at waist height. You have to climb a ladder a couple of steps, but I think you would be more likely to get a record prime given what happens to Mersins right now just from the math. Good luck.
All right. Thanks, Landon. I think we're gonna call it
Good
quits here. Thanks everybody for coming. And Landon, it's okay for me to post the recording of this?
Yes, you have my permission for recording. Put a record reference to the list, and if someone wants to get a hold of me, they can contact you, and I'll be happy to sit down and talk with them and answer if there's questions that you were thinking about and you forgot to ask, or you couldn't raise your hand or so forth. Fire them off. Be happy to give you some advice.
All right, thanks, Landon. This will be posted. His Landon slides plus the we'll put a link to where we store this on YouTube, so you'll be able to watch the video again if you want to take notes
and
again.
check out the full tutorials. There's a lot more details out
the
there
full
as well.
tutorial is incredible. I learned more number theory. All right, we'll see you all next month, and we're going back to AI again. So,
and congratulations.